we've spent some time covering different types of natural selection: sexual selection, artificial selection. And those are three things, but let's talk about actually four other things called the modes of selection. Now, I want you to keep in mind, any mode can apply to any type. So there are four different ways that natural selection can occur, and four different ways sexual selection can occur, and four different ways that artificial selection can occur. All of these modes apply to all of the types. I want you to be able to listen, define these, give examples. This, admittedly, kind of coming from Bio 142, but you look like you could use a bit of a break from the material we've been covering during the past two lectures. So let's look at these modes of selection. There are actually four, but most books will cover just three. And that's because the fourth is a little more complex. We know directional selection. So if we look at a directional selection, we start with a group of individuals forming a somewhat normal curve. This is how many individuals there are with each level of trait before selection, given a certain phenotype. The probability of survival is linear and increasing with increasing trait, or decreasing with increasing trait. Either way, it's linear for the directional selection, giving a certain direction that the phenotype will take towards a higher phenotype over 2 generations, or towards lower if the directional selection goes the opposite way. Stabilizing means you cut off the ends, so being too extreme in either way is going to reduce your fitness, so being more moderate is going to increase the fitness, and what that's going to look like is this kind of a hump right there, which is going to mean the phenotype's going to get snipped off at the ends in the next generation and kind of moved towards the middle. Now, disruptive selection means the extremes are what is chosen. So if you took a group of cats and put them they're either in a very cold environment or a very hot environment, then cold tolerant or hot tolerant cats would each survive at a higher rate, and then the middle cats, which don't really survive very well in either environment. And that is going to lead to disruption. It actually pushes down on the central phenotype's commonality and increases the extreme phenotype's commonality. And as you think of, this could actually lead to a disruption of the species, such that there are now 2 distinct phenotypes with intermediates having a lower fitness. So these are your 3 modes, kind of writ large, but we'll talk about the fourth in a few. First off, let's look at directional selection, some mice examples. So the directional selection here would be you have a bunch of mice, and they have a problem that the whiter mice tend to be more visible to owls at night. So whiter mice can be eaten at a higher rate. What this means is the lightest mice are always the ones chosen first and eaten. So this would mean that light fur, over time, kind of goes, these alleles for white fur kind of go extinct in the population, and you end up with darker mice in general. We've also seen this with the cranes way back when, where the cranes are picking out certain mice that were easier for them to find, or hawks picking up mice. It's just terrible to be a mouse. But the mouse fur examples are often examples of directional selection. You got 3 mouse fur examples right there with the cranes, the owls, and hawks, birds eating mice that are colored the wrong color for their background, because birds are very visual hunters, and mice come in a variety of colors. It's perfect. It's directional towards lighter or darker coloration depending on what the background looks like. Then you have stabling selection. So stabilizing. This would be perhaps where the mice are existing on a tan background. So this would be if the mice were white, they show up against a tan background. If the mice are dark brown, they show up against a tan background. But if the mice are tan, they don't really show up very well. So the extremes will be snipped off. This, just like directional selection, will decrease diversity in the population. So both of these so far decrease diversity by removing certain phenotypes that are less well adaptive, as it were. One good example of this, and I'm going to give quotes for a reason, and by the way, I'm watching a bird out my window right now, which is very appropriate because we're talking about bird predation. These are ball gulls on Solidago altisma, this northern goldenrod. And what happens to the goldenrod is it is pierced by a wasp, and the wasp's larva will make a little, fly. Urasta solidaginus, I should know this. It's a fly. The fly's larva is going to actually release certain hormones that make the goldenrod make a gall. Now, small galls can be pierced by a wasp, which lays its eggs in the larvae of the fly, and the wasp larva eats the fly larva and thus reduces fitness to 0. So wasps will feed on smaller galls. Woodpeckers will feed on the larger gull, drilling a hole through it and bringing out the larva. It turns out that larger gulls are indicative of larger larvae, and woodpeckers prefer a bigger meal. Wasps can pierce small gulls, woodpeckers prefer large gulls, so therefore you would expect that the medium-sized gulls are going to be the ones that will be selected. So we have your diversity before selection and then the diversity after selection. What you see is a gull diameter between about 20 and 24 millimeters is going to have the highest chance of survival. And the ones that have lower than 16 get eaten by wasps and higher than 26 are getting eaten more often by the birds. I call it an example because you would think the Eurasta solidaginis would over time produce gulls of the middling size. That it's not true. It's actually Solidago altissima that chooses gull size. So it's a plant that changes the size of the gulls, not the fly. So there is no natural selection actually happening over time because although there's selection on this trait, there's variability in this trait is zero heritable. So there's no actual endpoint evolution. It's just an example of selection that works pretty well, but doesn't evolve the population because no heritability. H squared equals 0. Okay, then you have disruptive selection. And it can be called diversifying selection, but that's fake. You're not really necessarily adding new diversity. You don't add new alleles really. You do increase how diverse the population is, but really just towards two extremes. That individuals from both extremes have a greater reproductive success. Perhaps these are mice living on a checkerboard. And the white ones and the black ones can each hide in their respective squares, moving diagonally, of course. And the other ones don't really match up well against the background and get chosen against. So this disruptive selection ends up with two distinct phenotypes, but does cut out the ones in the middle. Last is balancing selection. And that maintains diversity. Let's say you have these different butterfly types, because you do. So you have these different types of butterflies with different wings. Each species can have 4 wing morphotypes. Now the thing is, a predator will find one of these wing morphotypes and will discover that this is definitely an edible wing. So it'll, edible wing, actually an edible butterfly, of course, it'll look at the pattern on this wing, and the bird will choose to eat other things that have the same pattern because it finds out this one's edible, therefore other ones will also be edible. It's an easy thing for birds to do. It is most likely that the first butterfly that a bird runs into is going to have the most common wing morphotype. So if it has the most common wing morphotype, that bird is going to be rewarded even more by finding plenty more of these. However, it is unfortunate for the butterflies that have that wing morphotype because selection works against the most common. Selection works against the most common. And that means that whatever has the most common trait in this example is going to have the lowest fitness. So it's better to be different, right? This is also true in heterozygote advantage, where the malaria, the malaria protist, the Plasmodium falciparum, is going to select against individuals who have normal blood. If you have normal blood, it's easier for the malaria parasite to invade the blood cells, reproduce, and cause lower fitness of the individual who is now suffering from malaria. It turns out that the sickle cell allele causes the individual to not have normal blood, but also causes sickle cell anemia and thus kills the individual. So 2 normal alleles or 2 recessive alleles, and either way, it's bad for the individual and they will have lower fitness in the presence of malaria. However, in the presence of malaria, the heterozygote will have an advantage where natural selection is favoring having the heterozygous phenotype, where you have half normal, half not normal. And this means that this half normal, half not normal will not die of sickle cell anemia, nor will they have a likelihood of dying of malaria. So they benefit from having both alleles, and they will pass on to their offspring both alleles, thus balancing the selection and maintaining heterozygosity. We encountered this before when we discussed the cystic fibrosis allele in Europe and how that results in a lower number of cases of typhoid fever. So there you go for both ways. Then there's negative frequency dependent selection, like the birds I mentioned before and the butterflies. Here we have a fish that is being fed on by some scale-stealing fish. This P. microlepsis steals the scales from either the right or left side. In order to do so, it needs to actually have its mouth pointing towards the left or right side. A right-mouthed P. microlepsis will steal scales from the left side of a fish. And this is bad for the fish, and it will get hurt. So what it will do is it will start becoming more wary of things coming up from its left side. It's looking over its left shoulder. No, it can't. It doesn't have a shoulder. But it will become more wary, and right-mouthed P. microlepsis will have a harder time attacking fish that have learned from previous attacks of right-mouthed P. microlepsis. Whereas the left ones will then have a higher fitness because they are more able to get a meal. Once they become more common, of course, then the right-mouthed ones will have more of an advantage, and it switches back and forth over time depending on the sample year, as in the frequency of the left-mouthed individuals goes up and down around 50%, but never really escapes this because, if it becomes more common, it becomes less advantageous. Same is true for the influenza virus. We often vaccinate against the most common strains of the influenza virus, thus selecting against the most common. This is negative frequency-dependent selection because we are selecting against the most common phenotype. And that balances by maintaining a diversity where the least common organisms, the ones that dare to be different, are going to have a higher level of fitness. That's it. That's 3 lectures worth of dense material with H squared, S, selection on 3 traits. Think about that multi-dimensional thing. This is mathematically the most difficult chapter covered in evolution, and the test on it will be difficult because the math is difficult and the concepts are difficult. So go to Limeberry or go to Futai, whatever weather it is when you're watching this, and enjoy a treat for yourself because, you did all right, and go back through it, review it. It's tough stuff, but you will persist. You'll do that part of the selection that's good, right? The higher than the average. Anyway.